Now, on Tuesday, what we were discussing was the dipoles. I mean, and some of you were having questions about the dipoles. Why do we define the dipoles? Now, we had already seen charge. So a charge is something that creates an electric field that exerts a force on other objects. Now, if something doesn't have any charge, a net charge is equal to 0, that doesn't necessarily mean that it doesn't create an electric field. An example is what we call the dipole. So we had seen that although, for example, if we have some positive charge placed here, and a negative charge placed somewhere else, plus Q minus Q, now this whole system has 0 net charge. Nevertheless, it does create an electric field, especially if you are very close to this charge distribution, it has an electric field. Very far away, the electric field goes to 0 much faster than if this had a net charge, but nevertheless, it still has an electric field. So that is, in fact, you can just think of the next correction to the first term in the electric field created by any charge distribution would be due to the net charge. If the net charge is 0, then we have these corrections due to, now this is due to a separation of the charges. Now, a dipole forms when you have the positive charges accumulated around one point and the negative charges accumulating at a different point. Then you have this dipole. Now, you can even imagine configurations in which, for example, you put a minus Q over here, you put a plus Q over here. So if you look at this configuration has 0 net charge. The net charge is plus Q, plus minus Q, plus minus Q, plus Q. This is equal to 0. Now, if you calculate the dipole moment of this configuration, let's say this distance is d, this distance is d, let's say this is the x unit vector. You can say that, okay, the dipole, I have one dipole over here which has q, d, this is the magnitude of the dipole. The direction is from the negative charge to the positive charge, so it's in the minus x hat direction. Plus, I have another dipole over here. This is a 2-dipole system. This will be, again, its magnitude is q times d, but this time it's in the plus x direction. So this whole thing adds up to 0. This configuration has electric dipole moment 0. But nevertheless, this system still creates an electric field. And if you are, let's say, somewhere around this point, you will feel a net electric field. And just to give the name, the electric field will be proportional to what we call the quadrupole moment. And of course, you can, I mean, this is a kind of a Taylor expansion. The first term is the electric charge, then you have the dipole moment, then you have the quadrupole moment, and it can go up to infinity. And all these numbers would parameterize how your charges are distributed in space. Now, we will not be studying all these things in detail that you will do in your third year, but just to give you an idea, this dipole moment, the quadrupole moment, etc., just describes how the charge is distributed in space rather than the net charge. Q is just the net charge. It doesn't tell us anything about the distribution of the charges. But the dipole moment and the quadrupole moment are the things that describe us how charges are distributed. Any questions up to here? These two? Well, I mean, you can choose. I mean, if you have some, we already know the superposition principle, right? So you can say that if you have some charge distribution, the electric field will be the sum of the electric fields created by each one of the charges. So I just prefer to divide this charge distribution into two parts, the upper part and the lower part. You don't have to divide it like this. You can say that, okay, the left charges and the right charges, you can just divide it like that. That would also give you the dipole moment will also be additive. So if you divide your system in different parts, the dipole moment of the whole system will be the sum of the dipole moments of the parts of the system. So in that case, you will have some dipole moment pointing upward here, another dipole moment pointing downward here. In any case, the net dipole moment would be 0. But you don't, for example, in this case, you don't just say, okay, there is a dipole moment between these two, there is a dipole moment between these two, another one between these two, another one between these two. You don't do that. You first divide your charge distribution into separate pieces and sum the dipole moments of each one of the pieces. Now let's review our discussion about the electric field lines. Now if you remember our discussion okay, here. Now what we had said that rather than showing the electric field vectors at every point, we just prefer to use a sample of field lines. But of course the vectors carry two information. They have the direction, they have the magnitude. So this information we have to transfer we have to tell using the field lines. Well, the direction information was kind of easy. We could say that, okay, if you have any line, there's a tangent to it, and tangent at every point gives you two directions. You just choose one of the directions for your line, and that gives you the direction of the electric field. So that was kind of the easy part. Now the kind of more complicated part was how about the magnitude? And we said that, okay, we will draw the electric field lines such that the density of the field lines will be proportional to the magnitude of the electric field at a given point. So that is how we had defined the electric field lines. We had its directions. Its directions have to be tangent to the electric field vector at every point, and its density has to be proportional to the electric field line at that point. Now, we were not so much careful about writing this definition, though. You see, we define the density okay. We had defined this density as the number of field lines divided by the area. So for example, if we have an electric field lines, if they look like this, you can already say that, okay, the electric field line is strongest in this region, it is weaker in this region, just by looking at these lines. Now, how do we define the density? We said, okay, it's the number of field lines passing through an area. But let's say if you take such an area, and if you take such an area, this is A1, this is A2. You see, the number A1 is the area through which you have the electric field lines passing. So we have 1, 2, 3, 4 field lines passing through area A1, 1, 2, 3, 4 field lines passing through area A2. But obviously A1 is larger than A2. Although we have the same number of field lines, the area that they pass through is different. So it seems as if this density depends on how you choose your area. So this was the part that we weren't so careful about in making this definition. Now the proper definition would be number of field lines passing through a perpendicular area. So it's not any area. We have to make sure that the area that we are studying, you just take an area, count the number of field lines passing through that area, and this gives you the number of field lines, and then you have this area, you divide by the area, that gives you the density. So you have to take, when you are taking such an area, you have to make sure that it is perpendicular to your field lines. Now, there are a few ways of writing this thing. Let's see. We could have also made another definition. So let's say that this is our perpendicular area. Let's look at A1. Okay, this area is perpendicular, and A1 makes an angle theta with this perpendicular area. And then we can just say that A1 cosine theta will be equal to A2. Now, why? Let's take an example. I mean, is this clear to everyone? Why A1 times cosine theta is equal to A2? I mean, just think of them as if they are rectangles. Okay, they have the same base. Let's just put them like this. The area of the rectangle, any rectangle, is the base length divided by the width. So if you have these two areas, which make an 90 degrees angle between the two, the base lengths are the same, more or less. And the width, they just form a right triangle. And you see that if you consider this is the one side of the right triangle, this is your hypotenuse. So this side of the triangle, the length of this side, so this is our shape. All of this is a rectangle that points inside that goes inside the screen. This is another rectangle. You can just imagine this right triangle. If this angle is theta, now this is, let's say, A1, this is A2. A1 has this shape. A2 has this shape. These sides are equal. So if this has length A, this also has length B, A. Now this is length B, this is length C, let's say. On the upper shape, this is length B, and this is our length C. And just from that triangle, you see, no, this is, sorry. This is B, this is C. B is nothing but, no, C. Yeah. C is B times cosine theta. A1 is A times B. A2 is A times C. This is A1 cosine theta. Yeah, it's the projection, perpendicular projection. So going back to this example, okay, we said that, okay, when we are defining the density of field lines, first we said, okay, we have to take a perpendicular area, count the number of field lines that passes through that area, take the ratio that gives you the density of field lines, and hence the electric field, the magnitude of the electric field. Now we can release the condition that it has to be perpendicular, but this should be number of lines divided by area times cosine theta. Where we had defined this angle theta as the angle that your area makes with an area that is perpendicular to your field lines. This is how we define the density now. Now, of course, if you take a large area, large flat area, not everywhere the field lines will be perpendicular to that area, but so you have to take a very small area. So this, you have to think, just like when we were taking the derivatives, derivative was nothing but the ratio of two changes. Just in the limit that both of those changes go to 0. Just think of this like that limit. We will eventually take the limit that this area goes to 0. the number of field lines that passes through the area will also go to 0. The area will go to 0, but the ratio will still be constant. Now, this is our area. This is the field line that passes through that area, let's say. So we know that the electric field at this point is pointing in that direction. We know that the electric field is perpendicular to the field line, is tangent to the field line. And we were considering an area perpendicular to that field line. And this is how we define the angle theta. These are our definitions. Now let's also draw another perpendicular line, this time to, no, let us stick with this one. Now let me just do another thing. Let me draw a line perpendicular to my area. This is perpendicular to my area. And this angle over here is also theta. Okay. Now, what we had said, the number of lines divided by the area times cosine theta, this is proportional to our electric field, magnitude of the electric field. This is how we had defined it. Number of lines is proportional to the area, the electric field times the area times cosine theta. So that's the number of lines that we have. Now this is what we call the electric flux. We usually use this symbol. This is nothing but the electric field magnitude times cosine theta times the area. This is how we define it. This is a definition. It is, in a sense, nothing but the number of field lines, proportional to the number of field lines. And the proportionality constant you can just choose such that the number of field lines is actually equal to the electric flux. Any questions up to here? No, well, this was just to motivate that the electric flux is proportional to the number of field lines. I mean, I will not be using the number of field lines. I will be using this concept. And the fact that it is proportional to the number of field lines will be important in a moment. But the proportionality constant, I don't really care. The vertical area. Well, exactly. Your friend has well, I mean, original definition was the vertical area. But now we see that we could have as well done, just took the perpendicular of the component of the electric field perpendicular to the area. Now we can do that. But you see, before I was just playing with the concept of the number of field lines. Now, how do you define a vertical field line? That was kind of tricky, let's say. So I defined the density of field lines by using a vertical area. Now I see that I could have just, in the definition of the electric flux, this is nothing but the component of the electric field perpendicular to my area. Well, let's see. What's the unit of electric field? Remember, we define the electric field as the force per charge. What's the unit of force? Newtons. Unit of charge? Newtons per coulomb, or kilograms, meters per coulomb second squared. This is the unit of the electric field. And the flux? Well, this electric field times area, it is kilogram meters cubed divided by coulomb second squared. We will give names to them later on. Other questions? Now let's come back to this definition. So I have the electric field, which the magnitude of the electric field, the magnitude of a vector. I have also a cosine theta. So does it ring any bell, any rings? Does it resemble any other definition that we had, where we had the magnitudes of vectors and the cosine of some angle? Scalar product. So if you remember how we define the scalar product, if we have a vector A, a vector B, the scalar product is the magnitude of A, the magnitude of the vector B, times cosine of the angle between the two. So this is nice. I have the magnitude of A, the E, electric field, the cosine of the angle between what and what. So did we define the area vector with you? So does it ring any bells? What is the area vector? Well, this is kind of a motivation to define an area vector. I mean, I can write this as a scalar product. If this, I will define some new vector, area vector, such that this vector will have the magnitude of area, and its direction will be such that the angle between the area vector and the electric field is just theta. So basically, I will define this vector over here, S. This is the area vector. I will be using this quite often, so it's important that you understand it. Well, it would be nice to write this as a vector equation. Convenience, let's say. I mean, I know you still don't like the vectors. You rather avoid using the vectors, but that will be your life. I mean, get used to using vectors. You would like to use vectors, believe me. And that's what we will be doing here. So the flux, I will just write as E dot S. Well, it just matches. The scalar product will be nothing but the product of the magnitudes. The magnitude of this one is E, the magnitude of this one is the area. And the angle between this vector and the electric field vector is theta, cosine of the theta. So this is how we will define the area vector. Now, of course, there are some issues. It is perpendicular to the area. That's how we define it. If you take this one, this area vector is perpendicular to the surface, but we have two choices. We can we could have defined this S vector to be pointing in this direction, or S vector pointing in the other direction. It's completely up to you which one you choose. The only important thing is that you have to be consistent. Now, usually, I mean, when you have, we will be now discussing closed surfaces. So, if you just imagine this as a closed surface, you all have an idea about where is inside of this surface. Where is inside? Are you inside this surface or not? Depends on how you define the inside and outside. I mean, I can define the inside to be here and outside is everywhere else. In that case, you are outside. Or I can define that everything else is inside and this is outside. There's no reason to choose one over the other one. This is the boundary that separates the outside and the inside. The difference, So you are saying that this is also inside, outside, sorry. No, I mean, this is a surface, there's no inside the surface. Surface is very thin. Now the difference, the definition of whether you want to choose the outside as all of this space or inside this back or here is how you define this vector. The surface vector is usually chosen to point from inside to outside. So in this definition, if this is a, let's say, a closed surface, part of a closed surface, and you say that, okay, you are choosing the surface vector to be in this direction, you are saying that this part is inside, this part is outside. That will be more important in the soon. Now, of course, not all surfaces are so flat. I mean, what we are actually doing here is, I mean, if you remember on the first, in mechanics courses, we defined these line integrals when we were talking about the potential. We said that, okay, this is the trajectory. And what we did was we just gave this trajectory a direction, which mainly meant that if you divide this into very small segments, we could have defined this vector dl for each one of these segments, which was pointing in this direction. These are our dl vectors. As you go along your trajectory. We are, in a sense, generalizing this to 2 dimensions, to areas. Now what we have is we have these surfaces. Now this time it will be a surface of any size, any shape. You can imagine electric field lines in this region of space. And then if we want to calculate the total flux, that is, we want to calculate, in a sense, the total number of field lines that passes through this surface. Well, what we can do is, we already know how to calculate them given a flat surface. But this is not a flat surface. This is not a flat surface. But we can divide it into very small pieces, which will be almost flat. Now, all of these surfaces are flat. They have an area ds. And, well, I should also assign a direction to them. I can just choose upward to be my positive direction. So this will be my ds vector. And the flux would be, or the total number of field lines would be just the number of field lines that passes through each one of these patches. Over this surface. This is how we define the flux for an arbitrary surface. No, I mean, you can just imagine that I have these electric field lines, and here is my surface. They just go through. In 3 dimensions also, I have all these field lines. Just imagine them as if you have this water fountain that sprays water in all directions. Questions? Now let's do some examples. I mean, then probably it will be more clear. Now let's just assume that somewhere in space we have an electric field which has this shape. It has a, what's the magnitude of this electric field? Okay, you got the E0, you got the factor of 2. You got the factor of √2, but in the wrong place. It's not E0 over √2, E0 times √2. Is that clear? Why the magnitude is E0 times √2? Just take the scalar product with itself. This is E0 squared, x hat plus y hat, scalar product, x hat plus y hat. This is E0 squared. What is x hat dot x hat? X hat dot x hat is just 1. X hat plus y hat, 0. Y hat plus x hat, 0. Y hat plus y hat, 1. Now the magnitude is nothing but the square root of the square of a vector. And this is E0 square root of 2. Because I have 1 plus 1, 2. Now let's calculate the flux. Of course, then you have to ask through which direction, through which surface. Now let me take this surface. This is my surface S. This has side length L. This has side length L. Now what is the flux that goes through the surface of this electric field? Now if you see, this electric field is in fact pointing along this diagonal. So this is our X, this is our Y, this is the Z. So the electric field everywhere is pointing in this direction. The electric field lines are just straight lines in that direction. Now let's write the S. What is the S? It's in the Z direction. Well, we can choose it to be in the Z direction or the minus Z direction. It's up to you. Your friend preferred to choose the Z direction. Now, let me name this SXY. It's an area in the XY plane. It's in the Z direction. Well, since this is flat, I can just talk about the S vector because the perpendicular direction is everywhere the same. Or, no. Let's talk about the S. Of course, I have to take a very small segment. And what is the area of this very small segment? If this side is dy, this side is dx. Dx dy. So this is my ds. E dot ds, this is equal to, this is my electric field, this is my ds. It's 0. Z hat dot x hat, it is 0, they are perpendicular. Z hat dot y hat, it's also 0. So this is just 0. So the flux that goes through this surface in the xy plane is 0. it makes sense because this is the direction of our electric field. And you see, what we said was the flux that goes through a surface just counts the number of field lines that passes that crosses that surface. My surface is also horizontal. So my field lines do not enter this surface or do not leave this surface. So the total number of field lines that crosses my surface is 0. They are all tangent to it. That is why we have this 0 flux. Questions? There's no friction, there's no motion here. Until this point, the concept of the electric field is purely mathematical. Or this area itself is a mathematical concept. I mean, even this area doesn't exist. We are just imagining an area. I have this, I'm saying that, okay, I have the electric field pointing in this direction everywhere. And I'm just imagining this area over here. It doesn't exist. It's just a mathematical definition that we made. You just imagine this area. Sorry? E dot ds is equal to 0. Let's see, what is our electric field? It's given over here. And ds, we just said that this is z hat dx dy. The scalar product of these two vectors is 0. Because you see, x hat scalar product with z hat is 0. They are two perpendicular vectors. Similarly, y hat times z hat is 0. Now let me also write one more line here. This is the definition of the total flux. And what I have to do is divide this whole area into very small areas. The contribution of each one of these very small areas is E dot ds. And for each one of these small areas, E dot ds is 0. So the integral of 0 is just 0. Questions? You can use these silent times to ask your neighbor if you don't really understand something. Just ask your neighbor. Well, if you want to use the cosine, well, let's do it. Now we said E dot ds. This is equal to E, the magnitude of E, magnitude of ds, times cosine of the angle between the two. Now the magnitude of E is square root of 2E0. Magnitude of ds, this very small area that we had chosen, it is dx dy. Now cosine of the angle between the two. Now dx dy, you see this, here I have my ds vector. This is my ds vector. My ds vector is pointing like this. And this is my electric field. The angle between the two, this angle, 90 degrees, pi over 2. So cosine of pi over 2, this is equal to 0. Now let's take another surface. Let me choose this surface this time. a surface in the YZ plane. What is the flux that passes through this YZ plane? The same electric field. This is again E dot ds. It's integral. The electric field is E0 in the x hat plus y hat direction. ds. Now we can just imagine a very small area over there with sides dz and dy. So the magnitude of ds is nothing but dz dy, and it's in which direction? X or minus x. I mean, it will be up to you. You can choose it. The flux will change its sign, but at least in this example, that sign change will not have any consequences in the x hat direction. This is equal to, well, E0 is just a constant. I can just take it out of the integral. X hat dot x hat is 1. Y hat dot x hat 0. dz dy so this is E0 dz dy, but this integral dz dy is nothing but the area of this very small segment, and we are of this very small patch. We are summing over all of these small patches, but that gives me the total area. So this integral is nothing but E0 times L squared. This is the flux, the electric flux that goes through this area in the YZ plane. Now, if you want to do it with cosines, we can also do it in terms of cosines. Phi yz E dot ds. This is equal to the magnitude of the electric field, the magnitude of ds, times cosine of the angle between the two. The magnitude of the electric field is square root of 2 E0. The magnitude of the ds is nothing but dy dz. Now the angle between the two, this will be the, I mean, using this definition has the problem that it's not always easy to identify this angle between the two surfaces. Now if you go back to the figure, if you go back here, now this is my area. No, my area is here. This is my area. My electric field is pointing in this direction, in the diagonal. This angle over here is 45 degrees because of the particular choice of the electric field I have. So this is cosine of pi over 4, which is 1 over root 2. So this cancels this one, and I'm left with E0 times L squared. But you see, this is my, okay, this is the x-axis, this is the y-axis, no, this is the x-axis, this is the y-axis. My electric field is on this diagonal. It makes 45 degrees with the x-axis and 45 degrees with the y-axis. That is due to the choice of my electric field. This electric field, it makes 45 degree angle with the x and the y-axis. And the surface that I choose is on the y-axis. So it's why it makes 45 degrees. Other questions? True. True. I mean, your friend has a point. The flux need not, although we motivated the definition of the flux by saying that it is the number of field lines, the definition of the flux can be negative. If we had chosen, as your friend points out, if we had chosen this ds element to be pointing in the minus x direction, it would have been negative, the flux. Now, the sign you should interpret as, you said, when you are choosing the direction of in a surface, in an area, you are basically identifying the in and the out. The flux counts the number of field lines that go out. If there is an electric field line that comes in, that is a -1 electric field line going out. So that's how you should interpret the minus flux, negative fluxes. It's in a sense you can say that, I mean, you can talk about the flux of anything. You can talk about the flux of students that passes through this door. And here there is an area, if the student, in a minute, we will give a break and there will be students going out, so there will be a flux of students. And when they are going out, the number of students inside will be less. So the flux will be positive. When they are coming in, the number of students inside will start increasing, the flux will be positive. Will be negative, sorry. Okay. You have to be continuous. You see, eventually, you will take all these areas to be 0. The surface element, the surface direction cannot change discontinuously. It has to change continuously on the surface. We will do an example of that, don't worry. The magnitude is constant, yeah. The electric field is constant, we can just take it out. Sorry? No, I mean, I have a finite area here. It's just a finite area. Within this area, the electric field is just constant, so I can just take it out of the integral. Okay, see you after 10 minutes.